everybody. Can the people on the Zoom hear me okay?
Yes, we can.
Okay, great. Thanks so much for inviting me to speak to your group. My name is Dean Hartshorn, and I'm a master's student at Wesleyan in the Astronomy department. I'm finishing up here in just a couple of weeks. So I'm really excited to get this chance to talk about my research really close to the end of my project. Some of my earlier research interests dealt with the sun and the solar atmosphere. And I did a lot of outreach in undergrad related to solar eclipses. And that kind of ties in a little bit with what I'm going to talk about tonight, but only a little bit on the edge. So just to give you a brief outline of my talk tonight, I'm planning to introduce, what is the local interstellar medium? What's colliding in the local interstellar medium? How can we tell? And what does it mean? Why does it matter? Why do we care? So to start off, what is the local interstellar medium? The medium part is pretty easy. That's the stuff that's occupying space. Interstellar, in this case, just outside the solar system. And local is where things get a little bit tricky because there's a lot of different ways we could define local on the scale of, outside the solar system to the entire universe. What does local mean? And in this case, we draw that boundary right about at 100 parsecs, which is a nice even number. It means about 330 light years. But it's not just a random even number. It's a number that describes a distance in our local environment where things are different than the wider region. And I'll talk a little bit more about that. The space between the stars is not empty, and it's not the same. That means that there's stuff there, and the way that stuff moves, the temperature, its turbulence, its velocity, that's different in many different directions on the sky, depending where we're looking. And as we kind of move out from our solar system and into the neighboring space beyond, we talk about the local interstellar medium, or the local ISM is how it often gets abbreviated. We talk about it in the form of clouds of material that share characteristics. So we might say, okay, over here, we think we have a cloud of material that's all about the same temperature and it's all moving in about the same direction. And over here, we've got a different cloud of material that's a little bit cooler, or it's a little bit hotter, moving a little faster, and it's moving this other direction. And the thing is, when we're observing here on Earth and we're looking out into space, we might be looking through one or more of these clouds, depending on what direction we're looking at. They're not spread uniformly through space. They're kind of clumped up, or there's some spots where there's less of them. And that leads to some really interesting things for the way we take observations, as well as implications for the sun and the solar system and the environment that the Earth is moving in. So what's colliding? Well, you might guess that two of these clouds that I mentioned are the objects that are colliding, and that would be true as far as we can tell. The local ISM is made up of these clouds of material where the captions on this might be a little small to read, but in the center of this artist's map, this is not a real picture, it's just art. We have a picture of the sun, and we have an arrow pointing that the sun's kind of moving in this direction. And we have all of these clouds of material in different parts of the sky, and they're all moving in their own directions with these different arrows. And the two that I want to focus on tonight are called the Local Interstellar Cloud, or the LIC, and the Galactic, or G cloud. And those are circled here in red. And what you might notice is that the part of this map that corresponds to the Local Interstellar Cloud and the part that corresponds to the G cloud are kind of overlapping in the middle there. and that the sun is moving further into that region of overlap. So we have this situation where the sun is moving into this area where we have two clouds of material that have different temperatures, different velocities, different densities, and they're mixing. And we're kind of very slowly, but moving further into that. And so that's kind of the motivating question for my particular area of research is, well, what happens there? What happens in that region where we have these two clouds that are coming together, they're mixing? And what does that mean for both our observations and for our solar system? And that's all fine and dandy, but when you go outside with your telescopes and you're looking at a star in the sky, the only clouds that we can see with our eyes are the ones that are, ruining our nice star party, that are moving in front of our field of view. And those aren't the clouds that I'm talking about. Those are atmospheric clouds. They're mostly water, and they're here on Earth. These clouds are out in space, and they're really big and they're really hot. So why can't we see them? And part of the reason that we can't see them is because they emit primarily in the ultraviolet part of the electromagnetic spectrum. So they're at wavelengths that are too short for our eyes to see. And so how we get around this is a little trick of a technique called UV absorption line spectroscopy. And what that means is if you have a light source that's really bright, and you take that light and you spread it out based on its wavelength, you'll get a spectrum. And in the case of something like the sun, where it's emitting pretty constantly at all wavelengths, we'll get what we call a continuous spectrum. So something where it looks like this rainbow feature here on the left, where you've got a certain amount of brightness corresponding to a certain wavelength. And then we can draw this little graph here kind of showing how that changes as a function of the wavelength of light. Then if you have a cloud of gas, something where it's warm or hot, but it's not quite the same as like a star, right? That cloud of gas, it's not emitting evenly at all wavelengths, but it's emitting at really specific particular wavelengths. And we would see that in our data as these spikes that just pop up out of nowhere across our background there. Or if you were to look at it through a grating, if you were to spread that light out physically, it would look something like this black band here that has these bright bands of color interspersed throughout. But the technique that I want to talk about tonight, because it's the one that I use, is, like I said, absorption line spectroscopy. And what that means is, if you have a bright source and you have a cooler cloud of gas in between you and the light source, that cloud of gas is going to interfere with the light that you're getting from the star. It's going to block some of it. And the way it's going to block some of it is at really particular wavelengths that correspond to the materials that are in the gas. And that tells us a lot of information. We can use that to tell how fast the gas is moving, how hot it is. We can tell whether it's moving away from us or towards us, how turbulent the motions within the gas are. We can use it to do all sorts of things. But that's the underlying principle there, is we have a hot background star, and we have this cloud of cooler material in between us and the star. And so you might remember that picture that I showed a few slides ago of the sun moving through this region of clouds. When I'm getting data, what I'm using is, we've taken the Hubble Space Telescope, we've picked a bright star in the sky, and we are looking at the spectra that we get from that star, and we're looking for these really characteristic dips in its spectra here that correspond to those specific wavelengths. And because we see those as dips, instead of spikes, that tells us that there's something in between us and the star. So we know it's the local ISM. Here's a picture of what that looks like with some real data. This is one of the 4 stars that that my thesis is based around, HD 737 type 2, in case you were wondering. But what we have here is we have this, the light from the star is spread out by wavelength across the bottom here. And the light from the star actually forms this huge profile here, this whole thing that's labeled stellar emission, that's all from the star. With this particular element that I'm looking at, sometimes it can start to like absorb on itself, and you get this little dip right in the center that's marked as the self-reversal. And that's not an absorption feature in the typical way that we talk about it, but it does kind of interfere with our picture a little bit. But the thing I'm really interested in is these purple arrows, the ISM absorption, where it looks like a chunk has been taken out of this peak. I think I saw a hand in the back.
See your pointer.
Oh.
You can use mouse instead.
Oh yeah, that could work. Is this better?
Yeah.
Okay. So just to recap, the emission from the star is this whole background profile there. Towards the middle, sometimes we see a little bit of a dip right at the very center. But the thing that I'm most interested in is where it looks like there's been these little bites taken out of the spectra here. That's the ISM.
What wavelength of light is that correspond to?
So this is around 2,796 angstroms. So it's in the UV part of the spectrum.
In the UV.
Yeah.
So this whole graph is only 4 angstroms wide.
Yes.
Wow.
And that's really cool. And it leads into a little bit of what I think I'm going to talk about. Yes, I work with really high resolution data. I work with the highest resolution UV data that we can get. And I'll talk about that more in a little bit. So what we do is we take a spectrum like this and we do a lot of modeling of the size and the shape and the position of those absorption features. And that gives us information about what the local ISM is doing in that one direction on the sky. And the problem is the sky, as we're seeing it from Earth, is really big. And so if you want to get a complete picture of what the local ISM is doing all around us, you can't just look in one spot. You have to look in a lot of different directions, in a lot of different areas. And that leads me to my next point, which is that in order to map the sky, we need many observations. This picture here is a sky map. If you were to look out towards the center of the galaxy from your position on Earth and kind of picture the sky wrapping around you. So it shows the entire sky and it's kind of like unfolded and flattened. And the 2 clouds that are labeled here are the 2 that are colliding. We have the G cloud in green and the lit in purple. And the reason that the lit kind of seems to wrap around the edges is because we're inside of it, really. And so it covers a great deal of our part of the visible sky. And all of these little black dots are sightlines that have had their local interstellar medium analyzed in this way. So we try to get like pretty even coverage of the whole sky so that we can tell like, what it's doing. And the 4 dots that are marked in red here, 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 and here are the 4 stars that I have gotten to know really well over the last 2 years. They're the ones that we predict to be in that mixing zone, where we're a little fuzzy on where these cloud boundaries are. You can see that like this G cloud boundary, it kind of just follows these places where we have data, but there's a lot of places that we don't have data. And so around these borders, our knowledge, our model so far is incomplete. It's kind of fuzzy. But I use, as you commented, really high resolution spectra from the Hubble Space Telescope to study these 4 stars. And I love looking at pictures of the telescope because I think it really helps get an idea of the scale. So Hubble's been in space for 36 years now. And about 7 years into its time, the Space Telescope imaging spectrograph was installed. That's this picture on the right here. It's this big refrigerator-sized instrument that's being put onto Hubble during one of its servicing missions. This is just a picture of Hubble orbiting over Australia, which I don't know. I like seeing the little astronaut at the end of the arm and thinking about how precarious that must have felt. But so the Space Telescope Imaging Spectrograph, or STIS, as I'll call it, it's amazing. We get these really, really high resolution spectra. That means we can tell apart very tiny differences in wavelength, fractions of a angstrom, and we can detect across a huge part of the UV spectrum. So we can see things all the way from 1,200 angstroms to 2,800 angstroms, which is a really wide range. And the reason that we had to use Hubble data for this is because we actually can't collect spectra like this on Earth. The Earth's atmosphere is really, really good at blocking most UV light. And that's really good for your skin health, to keep you from getting sunburned. But it's not so great for astronomers who want to study in the UV. In order to get past that, we have to go to space. So just to give you a little idea of what it's like to work with Hubble data, Hubble data is taxpayer funded. And that means that it's publicly available. Anybody, no matter their institutional affiliation, or no matter, if they're an astronomer or not, is allowed to download data from Hubble. It's kind of a mess, but but you don't have to work at a really high profile university. You don't have to pay for it. It's data that belongs to all of us. And so for my research, like I said, I'm working with these 4 stars. So this is a screenshot of what it looks like to go and look for data there. You see I'm using the instrument STIS. This filter talks about the setting that I'm using, and it's a really high resolution one. The H stands for high resolution. And you can see that these were collected within the last 2 years. And then there's a bunch more information that isn't really as relevant. And then this is like the preview of the entire packet of data that I could get. And you can see it spans a really wide range. And you see these 2 big dips down here. Those are 2 of the strongest lines and features that I'm looking at. That's magnesium 2. And so those are kind of the really strong ones that we derive a lot of our analysis from. And that's all fine and dandy, but how do you go from a squiggle to understanding what the cloud is doing? And the way we do that is through something called absorption line fitting. And so this is just kind of all of the spectra that I've worked with on this project. And just to explain in a little bit more detail, this background jagged black line, that's the data itself. So it's plotted like that to help me remember that each one of those is a discrete point. It's not a smooth transition from one point to the next. And you can see some of these are a lot more jagged than others. And that has to do with that resolution as well. In order to tell what's missing in my absorption features, I first have to have a guess of what would have been there if there wasn't a cloud in the way. I need to approximate the star's emission without any other outside influences. And I do that with this blue line here, this smooth blue line kind of hard to see. Sorry about that. But in each of these little mini plots, there's this line that is my best guess of what the star's emission would look like if there were no clouds between us and the star. And then I use software that lets me try to fit the shape of those emission features one by one. I can say, well, what if there's one cloud between us? And what if it's, what if it's this broad and this deep in terms of the features here? And if I get a good fit with that, I can move on from there. But usually that's not the case. Usually I end up having to add a second cloud because there's often multiple clouds between us and a nearby star. But the further away you get, the more likely there are to be more clouds between you. And so each one of those components or clouds gets its own little like model of a dip. So in this one here, I have a little dip here, and then I have a bigger, deeper dip here. And then the red line that's overplotted is adding up the influence of all the clouds that I'm modeling. And so what I want most is for the red line to be a really good match to the data. That's the ideal. And we're able to do that with more or less success. But there's a lot of challenges in fitting absorption spectra. It's not super easy to see where all of the missing chunks are. Some of these are described here. Sometimes we have something called saturation, where the absorption feature is so deep that we can't tell where it ends because our detector just bottoms out. You can't tell if it's really at 0 or if it is like 10 points below that. You have no way of knowing because you're saturated is what we call it. And so that's the case here. Other times the absorption happens to line up at the center, which when I was talking about that self-reversal, can make it really tricky to tell what's a kind of a natural self-reversal from the star and what's the absorption from the clouds. And other times the absorption is way off on the edges of the profile where we don't have very much signal. And so it's really hard to detect it at all. Say that the absorption's in the wings or that there's low signal. And sometimes the clouds, they're moving close to the same speed. And so it gets really hard for us to tell them apart. They kind of blend together and we can't tell it that's one cloud or two clouds or three clouds. And that gets a little tricky. What you might have noticed here is that these are divided into 4 columns, and each one of these columns represents one of those 4 stars. And then the horizontal rows are different. They're different ions, different elements that I'm looking at. The top 2 rows are magnesium, and the bottom 2 rows are iron. And you'll notice that the challenges that I'm describing from one picture to the next, like most of them aren't experiencing all of the same challenges for all of the observations that I have. And that lets me combine observations in a way that gets around that. When we think about absorption coming from a particular cloud of material, we expect it to behave not exactly the same, but similarly, whether we're looking at the magnesium, whether we're looking at the iron, whether we're looking at silicon or carbon. And so we can use, if we get really good measurements from one of those, we can use that to guide our fitting of all the other ones. Because you can't have a cloud of gas where like the iron is moving at one speed and the carbon's moving at a totally different speed and expect it to be like a well-mixed cloud of gas. Like that just doesn't make physical sense. So we can use observations across multiple different ions to get better fits and better understand what's going on. Hydrogen gets even more complex because not only do we have to deal with, we have our normal stellar emission. This is actually all one hydrogen profile, this entire thing. And you can see we have these chunks taken out for ISM absorption, but then we have a spike in the middle. And that's actually from the hydrogen that surrounds the Earth. And so we end up with like all of these different layers when we're looking at hydrogen. There's also like a lot of hydrogen in at the edge of our solar system. And that causes another like big chunk to be taken out, but it's not the ISM, it's part of our solar system. And so it's really tricky to disentangle all of these things for things like hydrogen. But it can tell us a lot about the environment that the sun is moving through, and so we care a lot about it. And so that's still something that I'm still learning how to do, is how to deal with the hydrogen spectra, because there are so many more considerations. And so what we do is we take all of these measurements, we take some from really heavy things like iron, magnesium, we take some from really light things like hydrogen, and we combine those for a given star, a given sightline to a star. And that altogether lets us finally do something physical. We can finally determine something physical about what's going on in the cloud of gas. This is kind of a mess, I'm sorry. And the way we do that is we have one equation, and basically none of the things in this equation really matter. We're measuring the width of the absorption feature, how wide it is, how wide that chunk is. And we know how heavy the mass of whatever it is we're looking at, whether it be carbon, whether it be iron. We have a couple of constants. You can just throw those in. And then we have two things that we don't know. We don't know the temperature, T, and this symbol, psi. We don't know the turbulence. So if we only had one measurement and we plugged it in here, we wouldn't be able to find either one. We wouldn't be able to find T, we wouldn't be able to find the turbulence. It would give us exactly 1 point on this right-hand graph. Which, sorry, I'm like all out of order. This right-hand panel here shows the mass of all of the elements, the ions that I'm looking at. So we have light things like hydrogen, we have carbon, we have magnesium, we have heavy things like iron, and that's what's on the bottom axis here. On the vertical axis, we have the width of that absorption feature. So we can assign that width a particular speed, somewhere between 0 and 12 kilometers per second. We expect light things to move faster, to be broader in that way, and heavier things to be narrower or slower or less dominated by that by turbulence. And so when we have just one measurement, we have one of these points. And that can't tell us a lot. But as we add additional points, what that allows us to do, because we know the mass and we know we've calculated the width of our line, we expect the turbulence and we expect the temperature to be the same or really close to the same, no matter what element we're looking at in one particular cloud of gas. And so that means that those things aren't really variable in the same way, because we expect them to be the same. And what that lets us do is it lets us do some fitting kind of behind the scenes that figures out the best solution. So this plot on the left here, this is temperature across the bottom, and this is turbulence on the vertical axis. And every one of these striped regions that's kind of overlapping corresponds to one of those elements that I was discussing. So you can see we have iron here as this big blue swath, and that's kind of the possible values that you could have for its turbulence and its temperature based on our measurements of the spectra. And then you do that for every single ion, every single element here. We have carbon, we have deuterium, we have hydrogen. And you find one spot where they overlap really, really well. And that's where this X is here. And that tells us that the best fit that we have for temperature, in this case, is about 8,000 Kelvin. And for turbulence, in this case, is about 1.9 kilometers per second. It's right where those two, or rather, where all of those regions intersect. And that lets us really narrow down what's possible for the temperature and for the turbulence of this cloud. That was kind of a lot. Sorry. So my research project was to do that for 4 stars. And I was able to, I showed you most of the fits, and I was able to use those to come up with the physical properties to those clouds. And I was able to compare them to what our existing picture of the local ISM sky was. And I was able to find that, for example, this star here, HD 73752, it does match up pretty well with either the Lick or the G cloud, but to a point where I can't distinguish between the two of them. The values that I get are equally valid for either the Lick or the G cloud, which to me is pretty strong evidence of mixing in the region. Down here for HD 27274, we also have another case where it could be, that's nice, where it could be either the G or the Lick cloud, which is interesting. These other 2 points, you'll notice that they don't, this one here that's labeled blue, I'm really sorry for that being a red point labeled blue, but there's a cloud named the blue cloud. And we were able to detect absorption there. And then you can see that this red dot here for HD 52698, it's labeled Lick, but it doesn't fall into the known boundaries of the local interstellar cloud. And so what that tells us is that our model is not perfect in this area. It's got some missing gaps. What made this tricky in part was that a lot of our model's predictions for how fast the Lick is moving in a particular area and how fast the G cloud is moving in a particular area, those estimates were really close to begin with. They were less than 3 kilometers per second apart. And that's right about the limit of what Hubble can reliably detect and make that distinction between, which is another reason it was so important to get that really high resolution data. We couldn't do it with anything less than that because our lines would be blended to a point where we couldn't tell them apart. Oh gosh. And then for temperature intervals, I'm so sorry for this. I should have made a more friendly file. What this is showing is the shaded regions match our existing knowledge of 4 nearby clouds. We have Lick, G, Blue, and Origi. And they match our known estimates of the turbulence across this dimension and our temperature across this dimension. And then all of the points with error bars, those are the things that I observed. So for many of our points, I get something, I get a cloud where I can match the temperature pretty well, like this yellow one, but the turbulence is way off, way higher than expected. Or I get a point like this orange triangle up here where the turbulence matches the G cloud pretty well, the rest of the G cloud, but it's way hotter than the rest of the G cloud. And that's also confusing. In fact, out of my whole sample, I only had one point, this one here, which is one of the ones that I had difficulty saying, is it Lick, is it G? That's the only one that's really solidly a match for our existing knowledge of the clouds. And that's something that I'm still trying to like figure out an interpretation for. To me, it says that there's something interesting going on in this region where I think that there's signs of collision. I think that when we have these increased temperatures, these increased turbulence, we have these velocities that are really hard to distinguish from one another in an area where we previously knew that there was one really close to the other. To me, those are all indicators of collision. But it also, no, that was everything you just said there, sorry. It also tells us that our existing model doesn't fully capture the intricacies of what's happening in this region. There's weird things that are happening at these boundaries of the clouds. We had a lot of problems in fitting things that we don't normally have. And we also had these cases where it was really, really unclear. We got a very strong answer, but the problem was that answer would be equally valid for either cloud. And to me, that says that there's something, they have some similarities in that region, in that mixing zone. But there's still a lot that we're trying to understand. And why does it matter? Well, the local ISM it's our region of interstellar space, and it's pushing up against the solar wind from the sun that forms the heliosphere. So we have the wind, the solar wind from the sun pushing out. We have the local ISM pushing in, and they're interacting at that transition. And the local ISM, whatever it's made of, how hot it is, how high the pressure is, how dense it is, it can alter the shape of this protective bubble that we have from the sun by pushing in and causing it to compress, contract, or by allowing it to expand. And that's some pretty significant stuff, because interstellar space is not very friendly. There's lots of cosmic rays, which are these really, really, really fast charged particles that can cause a lot of damage to living tissue and to electronics. And there's all sorts of like really wide variations in temperature. Interstellar space is not very friendly. We like being inside the cocoon of the heliosphere. But other scientists have found that there are indications here on Earth that about 3 million years ago, the heliosphere was so compressed that instead of being outside the farthest edges of the solar system, that edge of the sun's wind stopped around where the Earth was. So not just the outer planets, but all the way in to about 1 AU, 1 astronomical unit, right where the Earth orbits. And that the Earth was, for a time, exposed to interstellar space.
Sorry, when was that?
About 3 million years ago. And then I think that team also thought that there was a second period a few million years prior to that where it had also been exposed, based on finding really specific elements that we couldn't account for with a solar system origin in places like Antarctica. And so what the local ISM is doing does matter. I mean, it's not going to matter on like the time scale of, your next vacation or the end of this meeting. But it does matter for the planet Earth and for the solar system to know what is going on. And let's see. Oh, that was the about 3 million years ago. We think that the Earth was exposed to the local ISM. And we don't fully understand what that means. We don't fully understand what it means for the sun to be moving into a region where it's a lot more turbulent, where it's hotter than we had previously expected. This also impacts our measurements of other stars. If every time you look at a star with your telescope, you're looking through the local ISM, because it's between us and every single star. And so if you're a scientist, how do you make sure that what you're seeing is from your star or your object and not the stuff that's in between? So one of our efforts is to provide a database where other researchers can enter their coordinates and look up, well, what's the local ISM doing there in that part of the sky? And then you can, subtract that off of your measurements and say, okay, this is from the local ISM. This is from my star or my other object. And we also think that, whether or not a star has its own version of a heliosphere, an astrosphere, whether or not it has solar winds, and whether or not how those are impacted by the local ISM. We think that has really serious implications for things like planet habitability. As I mentioned, like, interstellar space is not a fun place to be. And so we think that, if other stars are in regions where the local ISM is encroaching on them so much that their astrospheres can't push back, that could have really severe implications for whether or not they have exoplanets that can hold on to their atmospheres, or that can, have liquids, things that we think would be necessary for life. And I just want to close with like my own kind of personal stake in this, which is that Hubble is 36 years old and it's working pretty well. It's had a lot of servicing missions. It's cost a lot of money. It's also delivered a lot of science, a lot of really good science. And in my particular field, the local ISM, Hubble is the only instrument that can perform these types of observations. When Hubble is gone, we don't have another mission planned to replace that specific capability. There's nothing else that can collect spectra that are this high in resolution in this part of the spectrum. And so, the administrators of Hubble and everybody involved knows that Hubble is reaching a point where eventually something really important is going to fail, like one of its gyroscopes, or orbit is going to decay such that it's not stable. And so we're faced with a decision here. They think that turning point is going to happen sometime in the next 10 years. And they've got two options. They can either send a mission to Hubble to deorbit it, which means to have like a very planned descent into the ocean. Or they can send a mission to Hubble to boost it and to repair it. Those are the two main options. And then no mission can last forever. It's not something that can live in perpetuity. But it is a mission that is capable of being serviced. It's capable of lasting. And I think the real key thing to me is that I feel like this is a decision that should be made on the basis of the science and the feasibility, and not based on whether or not we have to decide between this and 17 other things that are also really critical. When administrators have budgets with absolutely no wiggle room, it makes it incredibly difficult to make decisions based on what could provide the most science. It makes it really difficult to use those resources in a way that's wise. We've already put Hubble in space, and it's been doing really well for a really long time. It's outperformed all its expectations over its lifespan. and it could do more. And I don't know if that's the right choice. I'm glad I don't have to make that decision. But I do know that over the last 2 years, there have been repeated efforts to request that the budget of NASA science be lowered pretty substantially by about 40%, which is a really huge cut to its science mission. Congress has rejected those cuts last year and continued to fund NASA science at about the same level as before. But it's important that if you want them to keep doing that, that people know that you care about it, know that it's important to you. Funding for science is really popular and across many demographics and across many political orientations, and it's kind of a unifying force for many Americans. But it's important that the people who get to make those decisions know that it matters. And so I just encourage you, if you have the time and if this is something that's important to you, to let your representatives know that you care about funding NASA science at sustainable levels.
Thank you.
Thank you. I'm happy to take any questions.
I have a question for you. The Voyager 2 mission is at the heliopause. Shouldn't it be able to provide you some data about the interstellar medium?
Yes, actually, I'm so glad you mentioned Voyager 2. Voyager 2 did recently become something that we could consider a local ISM mission. It does provide some data in the form of like these measurements that are taken in situ, so in the place where they're at. We learned that Voyager 2 had crossed the heliopause, the edge of the heliosphere, in part because its detection of cosmic rays went from being like pretty low and constant to suddenly really spiking. And that was the indicator that we weren't protected by the heliosphere anymore. We were in interstellar space. The problem with Voyager for this type of study is that, it's going in one direction out of the solar system. And I guess you could consider Voyager 1 as well, but going the other way. But also that it's not really designed to take these sort of longer term high resolution science images. At this point, it's kind of reaching the point in its lifespan where it's kind of hunkering down and coasting for a really long time. And so we do get useful data. And in fact, my mentor, Seth Redfield, one of his previous students was working with not Voyager data, but she was working with New Horizons data, so out past Pluto, as that kind of reaches interstellar space as well. And she was trying to feed that into our kind of ecosystem of local ISM measurements. But that's a great question. Yes, our interstellar probes can give us a lot of information about the local ISM.
So there's a question online, so I'll go first in the chat. So the question is, what is the process to get to use the Hubble? And perhaps related to that, could you clarify, did you request the measurements that you used, or someone else had done those measurements and just got the benefit of the data already being there?
That is a great question. So in order to request time on Hubble, you have to submit a very detailed proposal detailing why you want to look at a particular thing, like what the science justification is, exactly when and how long you need, a lot of things about the feasibility and the cost. And that's a very detailed process. The deadline for Hubble proposals for this cycle is tomorrow. So my mentor is, I think, a little stressed out tonight. But the data that I worked with was requested by my research supervisor, Seth Redfield at Wesleyan. And it was collected about, sometime in the last year and a half to 2 years. So it was proposed for even before that. So before I came to Wesleyan. the really cool thing about using STIS, the instrument that I work with for this kind of observation, is because its spectral range is so wide. Lots of researchers are using it for other things that aren't the local ISM. They're using it to look at all sorts of things. And when they do that, they're also getting the local ISM like for free in their observations. So that means that I can go back and I can look through observations that were collected for a variety of reasons. And if they're taken in the right filters and they have the right kind of type of background star, I could go and look at what the local ISM is doing along those sightlines. So it's really wonderful because we have really targeted studies like this one that my advisor proposed for. But we can also use data that other researchers have collected. And then it's like even more bang for your buck, right? You can keep doing science with the same resources, which is really cool. And you had a question.
Yes, I had a question. So these clouds are out there, you talk the whole diameter you're interested in is 100 parsecs, or is that the radius?
It's like a 100 parsec diameter bubble
Okay.
around the sun.
So yeah, 300 something light years. So when these clouds are colliding, you have any idea, I'm sure it depends how dense they are. What is that kind of collision zone? Is it, as much as a light year or something? And when can you say we're no longer in the collision, now just in this cloud?
That's a really great question, actually.
That's a research paper.
Collision is maybe a bit strong of a word because these things are all not very dense and they're pretty spread out. And so it's more like beginning to occupy the same space and sort of influence each other. But still not as much, smash bang fireworks. But as far as the extent of that interaction zone, that's still something that we're trying to figure out. So there's exactly the model that I work with approximates the clouds as uniform spheres, and we know that that's not the case. And so we know that they're not these perfect spheres of cloud. We imagine that they're more filamentary, or maybe they're more compact, but they are kind of, like Earth clouds. And so we're making a lot of assumptions there with how we think they move and how we define that region of overlap. And you'll notice, I mentioned that all 4 of these targets were predicted to be in the deepest part of the predicted mixing zone. And that was based on a bunch of other modeling. But, this one here, HD 57095, it didn't show any absorption from either one of them. It was, it doesn't appear to be part of either one of them. It's just kind of doing its own thing. For simplicity, I didn't plot all of the clouds that we know about, but the blue cloud does kind of cover this middle patch here.
And the other one that you read that says LIC, but it seems to be outside of the LIC. Maybe you're right. The other references not.
Well, the model that was made for this purple cloud only included the dots that are within it. And so at the time that boundary was drawn, we couldn't say, well, maybe it goes here, or maybe it goes here. With this point here that's not included, the black one, that means that it didn't meet whatever statistical threshold we had for including it as part of that problem. But the red point just wasn't observed yet, and so it wasn't included in that model.
Well, a good question. I
have a question that relates to
Bill, Bill, just hang on quite a moment. Somebody in the room was asking a question. You probably
Sorry.
couldn't hear him. So
Sorry.
hold on. Just
I'll speak loudly. So just referring to your data with velocity, I'm assuming that is from Doppler shift, that one of the.
Yes.
So when you have elements, the spectrum of elements is so narrow, how do you detect?
That is where we talk about the resolution limit of STIS.
so sorry,
sorry.
since they're having
Yeah.
trouble there, maybe.
The question was when some of my plots mentioned something being in units of velocity, the question was that was assumed to be derived from the Doppler equation, from that relationship, and that's correct. But how to measure such a tiny shift? And that's where, again, we really rely on having that really high resolution from Hubble, because we can detect like the very limit of what we can detect in that realm is it's between 1 and 3 kilometers per second. So it's very, very small. And that corresponds to a pretty small shift in wavelength. But we can detect it. And that's right at our limit there. So, but that's a great question. Yeah.
You want to go?
Yeah, can you track down with, like, in this study of interstellar medium, can you track down the origin of these different clouds? So like maybe this cloud is a leftover from the formation of the galaxy. This cloud came from the T-Tauri winds of that star. This cloud is leftover when this stellar nursery dispersed. Is that part of the study of ISM?
Yeah, the origins of the local clouds are an ongoing area of research. The prevailing belief right now is that in our really local area of space, we're in kind of it's called the local bubble is what they call it. It's an area where it's a lot less dense than most of the other ISM surrounding us further away. It's about 100 parsecs across. So other really convenient thing there. But we think that bubble and the material within it is the leftover result of a supernova that kind of spewed out a bunch of material and shocked a bunch of things, and like that created both these cavities and these clusters of material.
Bill, if you want to ask your question now.
Thank you. It kind of relates to the earlier question. There's a whole lot of variables that you're working through in order to try to detect the clouds, and I gotta wonder. I mean, for instance, your star, I looked it up. HD 73752 is a multiple star system, which suggests you have multiple classes of star emissions. And so, I mean, there's one level of complexity. Their own heliosphere has probably hydrogen and helium absorption from the star's photons, and then our own heliosphere as well has some of that filtering. So, and then the other part is, I mean, every star, even though that it's in the class, can have different abundance of elements that give a different emission pattern, a unique emission pattern for each star. But you're looking like in between those, like the differences of those patterns, and it doesn't seem like there's a lot of room for detecting the underlying absorption that you're trying to get for one, let alone multiple clouds.
That is such a great question. I'm so glad you pointed that out, because we can actually use this technique to detect astrospheres and the heliosphere. Because as you point out, those things are made mostly of hydrogen. Let me see when I was talking about this Lyman alpha hydrogen profile, and I was mentioning that this is pretty complex to deal with. All of the things that you just said are part of the reason why it's such a mess, such a hassle. If this were purely, hydrogen emission from the star, we would expect the stellar profile to be the full width of this plot and very, very tall, like exceeding the top of this. We'd see this big bell curve there. And in fact, what we see when we look at H alpha through, or sorry, not H alpha, Lyman alpha, when we look at hydrogen through this technique, we see that, I wish I had a slightly better profile to show you. It's nearly saturated here, down here. You get this extra spike in emission from the Earth's geocorona. And then you have ISM absorption, like kind of all throughout. And one of my collaborators is really, really good at this. His name's Brian Wood. What he can do is, we're not going to see the astrosphere or the heliosphere. It's mostly made of hydrogen, so we're not going to see it in the other lines that are things like iron or magnesium. So we use those observations to get a good starting picture of what we think the ISM is doing. In my case, we typically use magnesium because it's one of the brightest, one of the strongest signals that we have to deal with. And then you model your local interstellar medium. You subtract off this geocoronal emission because we don't care so much about that. And what you're left with is you have your prediction for what the star would look like in its background here, and you subtract off what you've modeled the ISM to be in the other ions. And if you're left with additional absorption, that is the key to unlocking whether or not you're detecting an astrosphere or a heliosphere, because the heliosphere is moving away from us along our line of sight. It's the solar wind, it's moving out. And another star, if it has an astrosphere, those winds are going to be moving towards us along the sight. They're moving in towards us. And that means that the wavelengths of that absorption is going to be very slightly shifted in opposite directions. And so if we are detecting an astrosphere, we would get emission that's very slightly blue shifted. It's moving towards us. And if we were detecting our own heliosphere, we would get this extra emission, or sorry, this extra absorption. I think I misspoke earlier. We get extra absorption on either side of this profile. And one side of it corresponds to the heliosphere, the other side, the astrosphere of the star we're looking at. And this collaborator of mine, Brian Wood, actually did take a look at that for all four of these. And in this sample, he didn't detect any heliospheric absorption. That happens sometimes. Sometimes it just doesn't appear in our observations. It's not totally uniform. And he also mentioned that at the distances to all of these stars, they're all about 15 to 20 parsecs away. It's really unlikely that we would be able to detect astroperiodic absorption. We've only been able to detect astrospheres within around 7 parsecs. So we have to be quite close. But you bring up a really great point that we can detect that hydrogen from other stars in the form of absorption. And it's really exciting when we do, because it's one of the ways that we have of confirming an astrosphere around another star. So thank you for that.
It's amazing work. So how long, can you tell us a little bit about how long you've been working on this project and how you broke it out?
I've been working on this project for about a year and a half.
One more question in here, I know maybe good time.
And a silly question, well, can you take advantage of the ozone hole and put it?
That I feel like that's probably considered. I know sometimes we can like fly above most of the atmosphere, like on a plane, and do some observations that way. But I think in terms of like long-term utility, it's easiest to just park something in space for a really long time. But
Hubble gets sparked.
yeah,
In the ocean.
yeah.
So we have one more question online from Bob Hammond. What's next for you after graduation?
That's a really good question. I wish I knew. If somebody else knows, that would be great. As of right now, the only thing I have plans going on after graduation is I get to go to a workshop in Boston where I get to learn more about the plasma processes at the edge of the solar system. So local ISM, heliosphere, kind of where those two things meet. And I'm really excited about that. But I wish I knew a little bit further beyond that. So
Applied in schools?
I've applied to many schools. So yeah, it's been a rough application cycle
Yeah.
for many
You have a preference?
people.
I know we're running late.
I applied to a lot of schools both in New England and abroad. And
We'll rate our congressman for you.
I am waiting to hear from UConn, so we'll see. But
Thank you.
thank you so much.
Dean, thank you very much.